Hey guys, so I'm going to run through these Newton's laws notes with you. We're just going to go through Newton's first law today, and then we'll do second and third later. So we got to cover a few initial things. The first thing we're going to talk about is force, and we usually use F to represent force, and it's the push or pull that one object exerts on another. So like in Star Wars, use the force, you're either pushing or pulling something in a direction. And we measure it in newtons after Sir Isaac Newton, who really coined all of this and came up with the rules. And it equals 1 kilogram meter per second squared. You don't need to know that. You just need to know that newtons is represented with a capital N, and that is our units for force. And the forces can cause a change in an object's motion. When you push or pull something, depending on a few different things, you're usually going to change the way something is moving. And we can have more than one force acting on an object at a time. In fact, almost in every single instance, there are several forces acting on everything, even if it's not moving. And so the net force is when you combine the forces that are acting on an object and you decide what the end result is. And we'll talk about that more here in just a second. So we have this stack of books here, and we are pushing on it. This way matches. With a force of 2 newtons. So we are pushing that stack of books with 2 newtons, which means that it should move that direction. But then we have another force acting this way of 5 newtons. So we have 2 forces that are fighting each other. And what we do is we just basically add them together. So you have to think of one of them as being positive and one of them as being negative. So if we're pushing with 2 newtons from the left and 5 newtons from the right, we'll get a result, once that disappears in just a second, of 3 newtons, and it's going to be pushing that stack of books to the left. So our bigger force is overcoming the little force, and what's left over is 3 newtons to the left. If we have balanced forces, let me move my head over here. Balanced forces means that we have forces that are equal in size and opposite in direction. So if I am pushing with a balanced force, so if I have 4 newtons coming from both sides, they kind of cancel each other out. There's still those forces acting there, but my object's not going to move because my net force is 0 because it equals each other. And then an unbalanced force is when we have one that is larger than another, causing motion in the direction of our bigger force. So this is when I had my 2 coming in from the left, and now I also add in 7. So I have 9 total newtons coming in from the left and 3 pushing back on it. So I have 9 over here and 3 over here. When they're pushing together, then my bigger force is going to win out, and it's going to be 6 newtons, and it's going to push those books off to the right. So in 1687, Sir Isaac Newton, who's just honestly really a cool guy, came up with 3 different laws, and that tells us how we describe forces that affect an object's motion. So his first law is that an object will move at a constant velocity until a net force acts upon it, which basically means an object in motion will stay in motion unless a force acts on it. So an object at rest will stay at rest, an object in motion will stay at motion, unless we do something to change that. So we also call this the law of inertia. And you can think about inertia as when you don't want to change what you're doing. So it's how we don't want to change our motion. And an example of this is when you slam on your brakes in your car, or somebody else slams on the brakes, because not all of you can drive legally yet. Then when you slam on those brakes, your body was already moving forward with the car. So you in your car moving forward, your car stops, but your body keeps going. And so that's when you pull against those seatbelts, because your body is like, no, I'm doing my thing. I'm moving, and I don't want to change that. And the more mass you have, so the bigger and heavier something is, the more inertia it has. And you can kind of think of this like almost like Indiana Jones when he's running away from the big boulder. Like, you can't just stop that big boulder easily. It's going to keep going and rolling down the hill. But if it was a little tiny rock, sure, we have enough energy to be able to stop that. So then there's a few practice problems on that. Let me pause this and get that open for you. Just kidding. We're going to do practice problems together later. So let's talk about different kinds of forces that can change an object's motion. So we have friction. That's kind of one of the most common ones that you're going to know about. And that's when you have a resistance where something doesn't want to move when two objects are in contact with one another. So the most obvious form of friction is something like sandpaper going across a piece of wood. It kind of like takes some extra push to get it across because you have a little force there that stops it. And then air resistance. This is one that you don't think of all the time, but is always affecting us because we're literally surrounded by air. And that is a resistance an object feels when you're traveling through air. So like when you're running into a breeze and like you feel it pushing back on your face, that's air resistance. Then we also have gravity, another one that is always on us, but we kind of like take it for granted and don't think about it. And that's the attraction that two objects have on one another. Now, we think of gravity mostly as like the Earth, and the Earth does have gravity, but so do we. So do two objects that are just right next to each other. It just kind of depends on which is the stronger one. So our friction is going to depend on three different factors. The rougher the surface, the greater the friction, which again, if you think about sandpaper, the harder it is, or the bubblier, rougher, I don't know, the grittier it is, the greater the friction, the harder it is to smooth out that piece. Whereas if you have like a sheet of ice, you can go sliding nice and easy. So these rougher surfaces like our sandpaper have micro welds, which are little tiny bumps. You can almost think of like concrete on like a sidewalk or a driveway where it's always a little bumpy, or popcorn ceilings. And those little bumps are going to increase the resistance. Then we also have the greater the force pushing the two objects together, the greater the friction. So if I have like a board and a piece of sandpaper and I'm just like lightly rubbing it, it's not going to have that much friction. But if I put a 20-pound weight on top of it and then try to move it around, then I'm causing a stronger friction because I'm pushing those pieces together harder. And then the greater the surface area of the two objects touching, the greater the friction. You can almost think about this like if you're trying to move a couch, it's easier to lift up one end and try to push on just like the two legs of the couch across the room than it is to do the whole thing flat and push it across the room. And that's just because we have more stuff touching, so there's more micro welds that are stopping our movement. So we have three different types of friction. Static friction is when we have forces on two surfaces and it's not moving past each other. So like when you set a pencil like on a flat surface and it just sits there, that's static friction. Nothing is happening. We're not moving anywhere. We're just sitting there. But it's keeping it there because if you were to put the same pencil on like a block of ice, you might see it slide around a little bit or like in a puddle of water. But when we have just enough friction to keep it still and not move it, that's static. Then sliding friction. So this is when you like go skidding across like an ice patch or something. Then that's when we have friction as we're moving past two surfaces. And then rolling friction is when something is rolling on the surface. So that's helping it to roll in motion, but also slowing it down at the same time, depending on the level of friction. So like a tire rolling down a hill. All right, then we have air resistance. And this is also called drag if you're like in the aviation industry. It's friction that happens in the air. And that's determined by your speed. So the faster you're going, the harder you're going to feel that air resistance. The bigger you are, the greater the air resistance. So if you're going to throw like, I don't know, a volleyball across the room compared to like a little golf ball, the golf ball is going to experience less air resistance because it's actually just coming in contact with less air. And then the shape. So the flatter the object, the greater the resistance. So if I have this piece of paper and I'm throwing it across the room like this, my air resistance is only coming in contact with that one edge. Whereas if I try to throw it across the room like this, then my air resistance is catching the entire face of the paper. And then we have our universal law of gravitation. So any two masses exert an attractive force on each other. Everything you see all around you has a gravitational pull on everything else around it. And this is going to depend on the mass. So the bigger you are, the greater the gravitational attraction, which is why most of the time we don't think about everything having gravity on each other, because the Earth is bigger. The Earth wins most of the time. And then the distance. So the closer we are, the more gravity we have on each other. The farther we are, the less we have. You can almost think of this like magnets. If you hold magnets really close together, it's kind of hard to keep them apart. But the farther away they are, the less you feel that pull. And then gravity itself is our force on any falling object. So every time I was doing this earlier today for my physics class, every time I drop these pencils on the floor, I have an acceleration because of gravity at 9.8 meters per second squared. That's an important number to remember. So make sure that you make that nice, big, and bold and colorful in your notes. And it doesn't matter how big you are. If I was to drop, I don't know, an anvil and like a feather, they're both being pulled down by gravity at 9.8 meters per second squared. The reason they don't fall at the same speed is because we have that air resistance. But if I was to do that in a vacuum, they'd fall at the exact same speed. And then we have terminal velocity. So if something is falling from high enough, I don't know if you've ever heard of the story of someone dropping like a penny from the Empire State Building and it like cracking someone's skull. Disproven by Mythbusters, because everything has a maximum velocity that you can reach while falling. So at some point we're going so fast that we can't go any faster when we're falling. And this is when your gravity and your air resistance balance out. So instead of having our balanced forces on the book where we're not moving this way, we can't go any faster because gravity and your air resistance are kind of going at the same speed. So we have a net force of 0, meaning we have no acceleration. So while I'm still moving, I'm not speeding up like with gravity or slowing down. I'm just kind of going at a constant rate, which is that maximum velocity we hit. Oh, so fun fact, humans can only fall at 118.06 miles per hour. We can't fall any faster because air resistance matches up with our gravity. All right, and that is the end of the notes for now. We will do practice problems tomorrow, so please make sure you have those done and turned into classroom. Thanks.